Product development and support is relatively easy when targeted toward a specific regional demographic. For example, a software application targeted toward German government institutions would not need to support the Mandarin language, Chinese formattings, and features. IBM EBCDIC and ASCII support the core characters primarily used in American and Western telecommunications equipment. At the time, there was not much concern for non US English variants or even other languages, since major tech companies were centered in America. This subject can be extended beyond software into just about everything. You can see this everywhere in the consumer market, from automotive all the way to consumer electronics. Products are made as region agnostic as possible, primarily through the use of multilingual packaging and instruction manuals. A speedometer on a car reads both imperial and metric units. Internationalization and localization is a huge subject in the field of architecture and civil engineering, for public transportation hubs such as airports, train stations, and ports with multilingual signage and higher degrees of accessibility. Here's a list of some digital examples of internationalization and localization. Film may be localized through the alteration for showing of certain symbols and designs deemed illegal in certain countries. Video game dialogue, speech, and text is typically localized through the swapping of dialogue with other voice actors of different languages. Music is commonly localized through dubbing or lyric changes to be made more appropriate for certain demographics. Different countries and regions from around the world have different economical and societal conventions that software must adhere to if we want it to be successful in said regions. Not taking these regional conventions into account may result in a potentially unusable experience. Some of these conventions include, but are not limited to, legal document paper dimension standards for printers, telephone number formatting, postal addresses and zip code formats, even accounting for the situation for regions not having these, monetary units, date and time formats, 12-hour versus 24-hour clock, which comes first, the day or month, and number formatting, such as should the radix point be a comma or a period. These conventions directly affect aspects of software such as character sets, selecting a character set containing the proper characters. Not really an issue anymore with the widespread adoption of Unicode. Documentation, for example, what languages the utilities man pages are available in, hardware device support, keyboards of differing languages, and user interaction such as typing Mandarin through the use of typing phonetics. Organizations such as government entities or even companies may mandate the use of certain conventions for use within their facilities. Extreme examples of these mandates can be found within the People's Republic of China. With India's border conflict with China in the Kashmir region, a proposed bill would make software applications not displaying or categorizing the Kashmir region as intended by the Indian government a crime. From an engineering standpoint, it should be pretty obvious that the least painful way to implement and accommodate various regional configurations is not through a codebase that handles every single possible configuration. Bloat and overhead would simply make executables too large to use. Instead, regional dependent portions of the project are separated into separate modules, being loaded at startup or runtime by the regional agnostic core. This is analogous to comparing Unix's codebase before and after its first port to the Interdata architecture. Initially, Unix was only implemented on the DEC PDP systems, with much of its codebase being architecture dependent, moving to a more C orientation soon after. Porting Unix to support multiple architectures forced it to separate architecture dependent and agnostic portions of the codebase, which introduced abstraction and APIs. As a result, porting Unix was as simple as compiling select architecture dependent files through the use of pre processing directives. Operating systems and many user space applications adopt this distinction of dependent and independent portions of code bases, where the agnostic core logic is combined with select regional configuration files and code for regional dependent software features. This includes, but not limited to, code allowing Chinese users to type Mandarin with phonetics. Building an application in such a way is known as internationalizing it. A more formal definition of internationalization would be the process of engineering or building an application to support regional or national languages, formatting, aesthetics, upon many other worldly settings. Applied to our Unix analogy, compiling our internationalized codebase for a specific target architecture would be the action of localizing the software to the specific architecture. In terms of regional support in applications, the process of localization involves the compilation or dynamic loading of regional dependent code or files either at program startup or runtime. Software that is modular and internationalized must provide a range of localization settings. The process of localization is simply the process of setting these specific configurations. For the Unix codebase, for example, pre-processing directives can be set to localize the compiler to a specific target architecture. User space programs provide localization settings for specifying language, currency, and pretty much all other social and economic conventions mentioned earlier. A specific convention or a combination of these settings are known as a local. These are essentially localization setting presets. Localizing an internationalized spreadsheet software to be used in Spain, for example, involves configuring its localization settings to the Spain local, which specifies Spain's language and conventions. For use within Mexico, we must localize the application to the Mexico local. Although many attributes would be similar between Spain and Mexico locals, such as language, economical conventions such as monetary units would differ, euros versus pesos. It's important to recognize both language and region when selecting local presets, as multiple regions speaking the same language typically have different conventions. You can even configure custom locals if you are an American who primarily speaks Spanish, for example. As you may have noticed, both internationalization and localization are pretty long words and annoying to type out, especially in technical documentation where the same word may be written out a million different times. DEC in the 1970s first coined the numeronyms I-18N and L10N as the shorthand, and it just stuck with the industry ever since. IBM and Oracle commonly package the two of these concepts into the term globalization. At the end of the day, however, they all pretty much refer to the same general concept. Although the two words are pronounced the same way, there are actually two distinct words of different spellings in the digital world. This is to differentiate terms relating to localization and internationalization from terms such as local variables or local user data, for example. It's vital one understands that local with a preceding E is in relation to globalization, while the naked local spelling with no preceding E refers to everything else we use the word local for. When reading through technical standards or traversing file systems, knowing the distinction can become very handy. We described local simply as preset configurations of localization settings offered by user space programs, though often you will hear the word local described simply as the local or the environment local, as if there's a singular high and mighty local above all others. This may sound a bit confusing at first, so let's take a step back and look at how applications know which local to use, a Japanese versus French local, for example. As we take for granted nowadays, Unix systems are multi user, multitasking systems, where people can perform work concurrently, even of different languages. Suppose that Johann SSH'd into a Unix host and created a new session. Johann is more comfortable working with his native language, German, in which he has configured his account to be German. So each time he logs into the host and creates a new session, he will be working in a German environment. Jack is another user working on the machine concurrently with Johann, only speaking English, however. Jack doesn't have to do much since everything pretty much defaults or falls back to English anyways in the digital world. Upon Johann SSHing and authenticating, a new session is created for him, spawning his default shell. The local for this default shell is determined by its encompassed environment, configured to Germany. Any program spawned by this default shell is to inherit the German environment of its parent. For example, the shell spawns a Firefox process which inherits the default shell's German local environment. Soon after, Firefox spawns a pop up window process, which in turn inherits its parent's German local environment as well. So the pop up window will still be German. Switching gears back to the default shell, Johann spawns a fish subshell from it, though he manually changes the fish shell's environment to be of an English local instead of a German one. Thus, any process spawned from this fish shell will inherit an environment where English is the local. The functionality of environment inheritance and custom local configurations are done through the use of environmental variables. When a program refers to its environment, it just looks at the set of inherited variables and their associated values. Users can modify their shell startup scripts such as Profile or bashrc to assign custom values to environmental variables, creating customized environments automatically, so to speak. Johann configured his account's bashrc on the host to automatically create a German environment each time he spawns a new shell, in which any spawn process will inherit this environment to refer to. This is very useful since we could set and forget environments, since it propagates to spawn programs and applications automatically. For the case where Johann was using his fish shell and decided to move to an American environment instead, he entered Fish's vard built-in utility as a means to manually alter his environment. As a result, any process spawned from his fish shell will use American conventions and English, for example. As we know, localization settings for programs are stored in environments, where environmental variables act as an interface to pass localization settings. There's an issue of standardization, however, as developers left to their own devices will create application specific localization interfaces, crashing system globalization as a whole down into the ground. POSIX standardizes the core essential interfaces that programs should use for localization. It standardizes the names of core localization and environmental variables and their applications. There's no capital punishment for writing an internationalized application not using these core POSIX interfaces, though it's extremely bad practice, and pretty much every internationalized program makes use of them. Some standardized C system functions may alter their behavior since they refer to these core POSIX environmental variable interfaces. Keep in mind that a program may provide application specific localization settings with environmental variables, though should do so as a superset of POSIX interfaces. Environmental variables are used for more than just globalization, though that's outside the scope of this video. Let's take a look at these standardized POSIX localization interfaces, which are named after their associated environmental variables. Each of these interfaces are considered a category of localization, hence the LC for local category in each of their names. Interestingly enough, these variables don't contain any localization information at all, such as monetary information, how numbers should be formatted, upon many other things. Instead, they contain the name of locals that do contain such information. In the context of POSIX compliant systems, locals are actually just files or directories where programs may fetch specific localization settings, such as monetary units, dates and time formats, character sorting, upon many others. If Johann would like to have his program be completely localized to German, he would have to set all these POSIX environmental variables to the name of the system's German local, for example. Why can't we just have a single environmental variable that announces which local to use for everything? Why do we have to have multiple? These are fair points, though dividing localization settings into these categories allow for finer control, enabling the mixing and matching of different categories belonging to different locals. Suppose Johann is remotely doing work in America on a banking server. He would like to continue working in German, though needs to do his work with American monetary and numeric formattings, preferring all other conventions such as date and time to be in German. All he would have to do is simply set LC monetary and LC numeric variables in his environment to advertise to internationalized applications to use monetary and numeric conventions of the American local. Locals on a system are generated or compiled with the POSIX standardized local def utility. Johann may compile his own local with the local def utility to have customized localization settings, though this may be a bit of a stretch in certain scenarios. In this situation, altering individual category variables to borrow attributes from different pre existing locals would work just as well. Compiling locals are great for when the underlying system doesn't already have specific formattings or conventions that's required to be supported in certain situations, or if you're a super user that likes to crazily customize every aspect of the system, though even that's a stretch. Although this mixing and matching of local categories is a great reason for having multiple category variables, the feature is not used much in practice, with everyone just setting everything to the same local anyways. This introduces us to two other standardized POSIX variables, namely LC all and lang. These were not mentioned prior since they don't correspond to a singular category of localization per se, rather acting as helper variables to make life easier. Setting LC all overrides all other localization environmental variables when set. This is the most common variable altered if a user wants to switch to another language, since it's a quick and easy way to change everything at once to a singular local. Lang is pretty much the same thing, though it's instead just used as a baseline for any category not explicitly set. This is useful if you still want the ability to configure categories individually. GNU programs such as GNU Core Utils, GNU VI Editor, upon many others, do localize according to these POSIX variables. Though the GNU ecosystem of user space software also understands additional variables as a superset of the original POSIX standard, as to extend POSIX's functionality. As this is a GNU-specific superset of the core POSIX localization variables, non-GNU programs may not interpret or understand these variables. Other non-GNU user space ecosystems may define their own superset of the core POSIX localization variables instead. The GNU user space environment is the most prevalent in the Linux world, so moving between two drastically different distributions, such as Debian-style and Red Hat-style distributions, all localization variables, including its extensions, should be the same, since they both adopt a GNU ecosystem. Compare this to Solaris, System 5, and maybe even Alpine Linux systems that don't even share a user space environment, especially local extensions of POSIX. Each user space ecosystems are standards of themselves in a way. Although POSIX does standardize core baseline localization variables along with their uses, the question of which locals are to be present on the system is the Wild West. POSIX considers this muddiness an implementation detail for the most part. On Linux, for example, what local formattings are available along with their corresponding attributes really depend on distribution and maintainer. Between different distributions, a given local is part of different packages, of different maintainers. Thus, there's no guarantee that two implementations or versions of the same local will have the same exact formattings and conventions, though this isn't really too much of an issue itself, since any difference would most likely be minute. It definitely exposes a level of ambiguity regarding which formattings and conventions systems support. As a whole, POSIX's main goal is to foster a common and portable programming environment between its implementations. You could rely on at least some standardized baseline of drastically different systems to work with each other. This ambiguity regarding which locals should exist infringes on this POSIX philosophy. Many shell scripts rely on the parsing of a program's textual output through pipelining commands together. As many system utilities are internationalized on modern systems, the formatting of textual output can vary between locals. This can potentially screw up parsing and cause undefined behavior. Here, we run the following pipelines between two different locals. Unix-like systems are pretty much free to do whatever they want, such as a minimalist Chinese-based distribution for embedded applications only supporting Chinese text formatting and conventions. This is an extreme but realistic example, as there are many goofy Unix-like implementations. This throws portability at the door when moving shell scripts involving complex text parsing from our hypothetical Chinese-based distribution to an English environment on a Red Hat machine, for example. As POSIX's main purpose is to define some sort of baseline portability between compliant systems, it does mandate the presence of at least one local called the POSIX local, also known as the C local. Every aspect of values and settings this local defines is standardized by POSIX. So when working with two differing Unix implementations, for example, we could always bank on falling back to the common C/POSIX local that is guaranteed to be present on all machines. If you're an English power user working on an English predominant software project, it's always a great idea to set to the POSIX/C local, even though the American English UTF-8 local has become more or less a standard in of itself because of how popular and widespread it is. There's no capital punishment for not setting to the POSIX/C local, though it's good practice since each aspect and detail is standardized and guaranteed to be present on every system. Locals define a lot of aspects of localization, though not all of them. They specify formattings and conventions relating to money, dates and times, numbering, CLI acknowledgments, upon many other things. Aspects of localization not relating to formattings are outside the scope of locals. These include, but are not limited to, textual translation, localization of user interaction, such as region specific menus and options, hardware support for keyboards of differing languages, and countless other things. These notes are geared toward terminals and text-based utilities. In this regard, localization primarily just encompasses formattings and textual translations. If anything, locals at most really tell the application which target language should be used for textual translations, though don't contain any application-specific translations themselves for obvious reasons. So in this regard, language localization features are really left to the individual programs to implement for themselves. Pretty much all internationalized software make use of libraries to offload the work of language localization. Some common libraries are POSIX catgets API, getText API, Microsoft's LoadString library, and Qt Linguist for GUIs that make use of Qt. In the context of language localization libraries, a message is simply a string of text to be translated, or in other words, a string of text returned by a translation function. These libraries rarely perform any actual translation, instead referring to message catalog files that contain a range of available messages to use. Each message catalog file is tailored to a specific language, so library functions must read the correct ones. As there can be countless versions of message catalogs, message databases exist to organize the numerous message files present on the system. Talking about making codebases modular and portable, offloading language localization to libraries and resource files separates developers from localization maintainers. It's common practice to contract out the translation of application messages to contractors that return the proper catalog files. Though now, that can be achieved just as well with using AI. This allows internationalized development with very limited linguistic knowledge. Since these notes are geared toward Unix-style text-based environments, we'll limit our focus to catgets and gettext libraries. As the universal character set was in development in the late 1980s, there was a growing push to internationalize software. Up until then, it wasn't really a concern on anyone's mind, and standards organizations never really touched the subject themselves. As we know, whenever anything in the digital world isn't standardized, it usually becomes an implementation Wild West. With different programs using different APIs, different message file formats, and different message databases. These ambiguities aren't good for software portability. As a response, the X-Open Portability Guide, or XPG, standardized the catgets API in 1987, in which all XPG-compliant systems must support. The XPG is an extension of POSIX that evolved into the Single Unix Specification, or SUS, as we will describe in Unix history in another video. Eventually, the catgets API was officially adopted into POSIX itself in 2001, rather than being specific to one of the many extensions of POSIX existing at the time, including XPG. Thus, every 2001 POSIX compliant system must support the catgets API. As we know, there's no capital punishment for programs that don't use standardized interfaces such as catgets, as it's really up to the programs and developers in how certain features should be implemented in their programs. Rather, these interfaces serve as a common baseline that are guaranteed to work between implementations, available to any application that wishes to use them. CatGet's adoption has diminished throughout its history, essentially being a dead API as of 2024. Some microsystems decided to create their own internationalization library called gettext for their proprietary Unix-like operating systems in 1993. Although POSIX required their systems to support catgets, these Sun OSs provided their new catgets API alongside the mandated original catgets. This new Sun internationalization library was quite popular since it was easier to work with compared to POSIX catgets. The GNU project decided to create their own spin of the gettext library as a free and open source port. This is comparable to how the GNU project created open source implementations or spins of many common proprietary Unix software, such as the core utilities, Bash, gzip, GCC, upon many others. GNU's implementation or spin of the gettext library added additional features and functionalities that made it even easier to work with than the original Sun implementation of gettext. Most notably, the key as string feature. This is a unique feature, as many other APIs or libraries would instead require the use of numeric keys, which quickly became too much for programmers to keep track of. This ease of use made gettext an even more appealing option compared to POSIX catgets. The free and open source Linux kernel quickly became a viable choice when choosing implementations of Unix like kernels, soon becoming the choice. Although nowadays you could run the Linux kernel with a non GNU user space environment, the GNU ecosystem is still the most prevalent across distributions. Whichever machine you log into or distribution you look at, chances are that it's using a GNU user space environment. In early Unix history, the GNU user space environment was pretty much the only viable option you had. With Linux becoming the Unix-like implementation of choice, in combination with the fact that the GNU user space environment was really the only viable option at the time, GNU gettext's adoption spread like wildfire. How other non-Linux Unix-like systems implement internationalization APIs don't really matter, since these nodes are geared toward Linux-based systems. The world essentially transitioned from heavy competition between Unix implementations in the 1990s to heavy competition between Linux distributions instead. Canonical's Ubuntu versus IBM's Red Hat Linux distributions in 2024 compared to HP UX versus Sun's Solaris of the 1990s and early 2000s. As we may have hinted about the digital world, non standardized areas always become the Wild West, fostering portability hell. In the contrary, quite the opposite is true in many situations. Sometimes various implementations of a thing synchronize with each other, creating unwritten rules and standards. These synchronizations are primarily formed with the mindset of everyone is already doing something a particular way, so I should do it as such, which forms unwritten rules and standards in a way. A perfect example would be the various clones of the IBM PC. IBM's BIOS was independently developed, proprietary, and did not conform to any existing standards per se. Competitors used the cleanroom method to reverse engineer IBM's chips to create their own BIOS implementations, having identical interfaces as IBM's. The BIOS interface soon became an unwritten standard or convention that all PC manufacturers had to abide by. Not conforming would result in incompatibility with existing software, leading to financial losses. This formation of order in the midst of chaos is in a way analogous to getText's adoption. As BIOS was never originally developed to conform to any standard, its interface inadvertently became an unwritten industry standard. POSIX nor any of its countless extensions mention getText at all, due to the combination of 1. Linux being the Unix-like system of choice, 2. GNU user space environments being most prevalent on Linux systems, 3. GNU user space environments offering the more appealing getText API alternative. It's become an unwritten standard in a way that getText be used as the internationalization library for just about everything. Although there are many holdouts, getText has dominance in the text utility world, with many applications such as Graphical GNOME using getText as well. Though in the graphical world, applications are a bit more versatile, since some may use the Qt Linguist library, for example. Due to getText's use becoming an unwritten standard due to its widespread traction, even Linux distributions not utilizing a GNU user space environment even support the API, such as the Alpine distribution. Its Muscle C implementation of libc supports the getText API. The getText API is even available in other languages such as C++, Python, Perl, upon many others. Exceptions include Java, which has its own spin on internationalization and just about everything else. In 2019, there was heavy debate of whether to include a getText API as part of POSIX, considering its virtually universal adoption and its fallen foe, catgets. Unfortunately, this integration never happened. I believe it would have been a beneficial formality. Although we have portable catgets, no one uses it, and portability of programs using getText bank on the unwritten standard or rule that systems are expected to support it. In a way, it feels like the whole thing is hanging from a thread. We said earlier that different user space environments across OSs have their own spin or implementation of getText. This is more or less an accurate description. More specifically, it's the standard library portion of the user address space environment that actually provides the getText C API. So we'll limit the scope down to that for this section. libc's core structure is defined by the C standard. POSIX defines certain features that should be available on all compliant systems, mandating the availability of certain associated APIs. So, libc implementations add these POSIX APIs on top of the core C standard APIs. Finally, there are the non standardized APIs, where implementations add their own specific stuff because they feel like it. These are libc implementation specific, with no guarantee of portability between them. GetText is not part of the C or POSIX standards. Whenever there are informal expectations that certain non standardized APIs be present everywhere, they are always categorized as implementation specific, despite the fact that it's present everywhere. A weird yet understanding phenomena. The C, POSIX, and informal standards only describe front end APIs, leaving the inner workings side of things to libc implementation. glibc and musclec have many of the same function names, though their underlying code and inner workings are drastically different. The use and behavior of these APIs are well defined, allowing programmers to lazily turn a blind eye with the excuse of saying, oh, that's just an implementation specific detail. This is not an inherently bad mindset, as it works for most APIs programmers use. Some libc APIs, however, are more involved than just mere code differences that developers can lazily ignore in the name of abstraction. Some APIs, such as getText, require more from libc implementations than just underlying code, but expect them to additionally supply entire environments. For example, environments provided for the getText API involve reserved directories on the file system to store localization archives. We will discuss these later on. As these API environments are provided by libc implementations, the structure is libc implementation dependent as well. For example, in 1993, Solaris's libc may have reserved different parts of the file system for getText in comparison to GNU's libc. In these notes, we will discuss the GNU's implementation of the getText API and associated environment, as it is the most common amongst systems. Local and local def utilities are core to system globalization. To better understand them, we need some background. The glibc implementation is more of a suite rather than a standard library. It consists primarily of these 6 parts. Libraries, headers, and documentation are common to pretty much every library out there, though the inclusion of utility artifacts are interesting. Let's take a look at these utilities provided by glibc. A portion of these utilities are actually POSIX standardized utilities. While looking at the list of POSIX defined utilities, you may notice that almost all of them are implemented as core utilities on most systems. Here we see the files of Debian's core utility package. This raises a great question. Why are some POSIX utilities part of glibc when the vast majority of them are categorized as core utilities? Why are POSIX standardized utilities part of libc rather than having everything be core utilities? The utilities that fall within the core utility category are more so meant to provide a standardized shell environment for users. These utilities don't affect libc API internals at all. Why should programs such as sed or date alter libc API internals? The most they do is use provided libc APIs without touching any internals. As mentioned, there are some APIs provided by libc that require more than just underlying code to implement, but entire API environments as well. For example, libc implementations of the iconv and getText utilities have their own associated environments on the file system. Some standardized POSIX utilities' sole purpose is to modify these environments to purposely alter API behavior. For example, POSIX mandates the use of the local and local def utilities, whose intended purpose is to configure internationalization environments provided by libc implementations. As mentioned earlier, the structure of these provided environments are libc implementation dependent. This entails that any program modifying such environments are also to be libc implementation dependent as well, raising portability concerns. Technically, such utilities can be designed to be generic and run in different libc modes. Configuring and tailoring generic utilities with target libc implementations would be too much of a nightmare. Instead, having such utilities come with the glibc implementations themselves guarantee that they will always be compatible. There is another reason why such environment modifying utilities are not core utilities. Core utilities only make use of front-end APIs, not touching API implementation details for reasons of portability and reduced complexity. Utilities touching API implementation specific details will make horrible core utility candidates, such as POSIX local and local def utilities. As we see, not all glibc utilities are defined by POSIX. Most of these GNU implementation-specific utilities are actually just helpers. For example, the iconv is a POSIX standardized utility, which is pretty straightforward to use when looking at both its open group and GNU-specific manual pages. As we see, the glibc-provided environment that implements character set conversions are the following directories. The iconv utility itself is only really meant to use this environment, not to configure it. glibc provides the GNU-specific iconv config utility as a means to configure its character set conversion environment. Local def and local are similar, though both are POSIX defined. The local utility only uses or reads the system's internationalization environment as a means to print useful information to the user. The local dev utility is more meant to configure the environment. For the most part, POSIX and its countless number of supersets only care that standardized utilities are present and ready to use via the shell. They don't really care whether a utility or interface should be a core utility, libc implementation, or part of another library or package, as long as they are present and available for use. As a result, different Unix-like systems may place things in different places. Everything discussed here on out will be GNU specific. We will continue these globalization notes in the next video.